review some standard univariate probability distributions that occur frequently in practice. Univariate means that they're functions of one variable, x, and the distribution tells what the probability of x should be. A bunch of these distributions are roughly bell-shaped, so we can group them together just by that property and talk about them one by one. So here's a picture of distributions: the normal distribution, which is the solid line, and also, as you see, as the fastest decaying tail, and then several other student distributions, a logistic distribution that we won't discuss, and the Koshi distribution that we will discuss, which is this guy here, whose tail is noticeably larger as we go out to extreme values on both sides. So first, the normal distribution. This is probably the most important single probability distribution. We'll find out why a couple of segments from now when we discuss the central limit theorem. The normal distribution is also called Gaussian, and if you draw a value x from that distribution, I think this is the first time we've seen the notation, which is read x is drawn from a normal distribution with mean mu and standard deviation sigma, where sigma is some parameter greater than 0, then x has the probability distribution given here. It's an exponential in the square of the distance of x from its mean divided by the standard deviation. And then you have to remember that there's this minus a half in front. The factors in front are just the normalization factors that are needed to make this distribution have area under the curve equals 1. If the normal distribution is a family's best behaved child, then the Koshi distribution has got to be that sibling who's always getting into trouble. The Koshi distribution, which we write as this: x is drawn from Koshi, and Koshi depends on two parameters, mu and sigma, which is something like its width, greater than 0. Anyway, x is drawn from Koshi if x has this probability distribution. Now let's see what's going on here. Just like the normal distribution, we're looking at the squared distance of x from mu measured in units of this width sigma. But instead of now having the distribution fall off exponentially in this distance, it's only falling off as a power law. In fact, it's just 1 over 1 plus this quantity in here, the square. Again, the factors in front are necessary to normalize the area of the distribution to be 1. Now Koshi, which is also called a Lorentzian distribution by physicists, the Koshi distribution is a perfectly good probability distribution. It has area equals 1. What's odd about it is it doesn't actually have a mean or a variance or standard deviation. If you plug this formula in and try to do the integrals, you'll find that the integrals are divergent. So mu is not the mean. Mu is the center of the distribution, but it's not actually a mean. And sigma is some measure of the width of the distribution, but it's not actually a standard deviation. We just have to live with that. There's a univariate distribution called student's distribution, which now depends on 3 parameters. T is drawn from student distribution of nu, mu, and sigma. Mu and sigma are either the mean and standard deviation, or if those don't exist, the center and a measure of width. Nu, the parameter that's been added here, is just a power in the power law. In fact, student generalizes the Koshi distribution, which had pretty much this in it before, but instead of the -1 power, which was in the Koshi distribution, we now allow this power to be set by the parameter nu, and conventionally it's done in this way. The only extra wrinkle, again just a convention, is that Koshi is also defined, student is also defined with a 1 over nu here in the squared factor here. And what's all this stuff out in front? Gamma functions, the gamma functions come in when you do the integral of this to normalize the distribution, as well as the square root of nu pi and the 1 over sigma. So this is a bell-shaped distribution. We saw a couple of examples in the figure a couple of slides ago. But you now get to specify by the parameter nu how fast the tails should fall off. It's obvious that Koshi is a special case of this. You can just plug in nu equals 1, so that here we have 1 plus 1 divided by 2, and that's the minus 1 power. It's a little less obvious that the normal distribution, which is the exponential, is also a special case of the student distribution. That's the special case where nu goes to infinity. And this has all been cooked up so that even as nu goes to infinity, this whole expression goes to a perfectly good function, in fact a function with mean mu and standard deviation sigma, and it becomes the normal distribution. I'll leave it as an exercise for you to work that out. It's not very hard to do. Note that sigma is actually not quite the standard deviation in this formula. It turns out that the variance is the parameter sigma squared, but then there's this factor nu over nu minus 2 in front. So as nu becomes large, then it does become the standard deviation. This also tells us how small nu can be for the standard deviation to exist. The smallest value of nu, you can see, is somewhat epsilon larger than the value 2 if the standard deviation is to exist as a moment. Nu can go all the way down to 0. Nu equals 1 is the case of Koshi. These power law distributions, or rather these bell-shaped distributions that have power law tails, are called heavy-tailed distributions, and we'll have some important uses for them in later segments. You might wonder where the student distribution got its name. Is it named after someone named student? No. Is it named after someone who was a student? Well, yes, but only in a certain sense. Student was actually a pseudonym, a pen name, of a famous statistician whose name was William Seeley Gossett. Gossett spent his entire career at the Guinness Brewery in Dublin, where he rose to become the company's master brewer. Gossett didn't think that his employers would like to see his affiliation listed in journal articles that he published, so he published under the pseudonym Student. You might think it's odd that a brewer should be a famous statistician, but in fact, brewing was one of the first exact modern manufacturing processes. In brewing, you try to make every batch of beer come out exactly the same, even when there's variation in, for example, the starch content or sugar content of the grain that goes into it, or in the processes, or in the yeast. So brewing, in a certain sense, was the original high-tech industry in the late 19th and maybe the turn of the 20th century. Let's turn to a different set of distributions. These are related simply by the fact that they're frequently used probability distributions on the half line, on positive x. The one that's a little bit of an oddball in this picture is the monotonically decreasing exponential distribution, which is this dashed dotted line here. The exponential distribution, as the name implies, just falls off exponentially. So if x is drawn from an exponential distribution that has one parameter beta, then its probability is simply e to the minus beta times x, in other words, falling off for large x. Beta controls how fast it falls off, and for larger beta you can see it falls off faster, for smaller beta it falls off slower, and the beta in front here has to be there to make the area under the curve, the integral of p of x dx from 0 to infinity, be equal to 1. These other distributions now are a little more interesting. The log-normal distribution is simply the normal distribution of the log of a quantity. So on the positive x-axis, if we take the log varies from minus infinity when x equals 0 to plus infinity when x goes off to infinity. So we can say that if x is drawn from a log-normal distribution with two parameters as usual, a parameter that tells where the center is and a parameter that tells what the width is, then the probability distribution is defined to be this. You can see that it is a Gaussian, a normal distribution, but in the log of x here, not in x itself. Now when you look at the normalization, you see something a little peculiar that we need to explain. These factors, the 1 over the square root of 2 pi and sigma, come from the normal distribution. But there's this additional 1 over x in front. Where did that come from? Aha, we're writing here a probability distribution of x. But what's normal about this is that it's a probability of log x d log x. Now d log x is dx over x, and that over x is the source of the x here. You need it to make the normalization come out right, and you also need it to make this distribution truly normal in the log, p log of x, d log of x. Now, mu and sigma are the mean and standard deviation, the actual moment mean and standard deviation, in log x space, but they're not the mean and standard deviation in x space. Those are given by these peculiar formulas, e to the mu plus a half sigma squared, and I won't read this one out, but this complicated combination. This might be a good place to show how you don't have to memorize formulas like this. You don't even have to know what book they're found in, because you can just compute them in a language like Mathematica, or also probably MATLAB, symbolically whenever you want them. So let's go through that exercise to get a little bit of extra use of Mathematica. Here we write down the distribution of interest. P is equal to this thing, which should be an exact translation of the distribution right up here. And we want to find its moments, maybe the first 3 moments. So we're going to integrate 3 different integrands here in a little vector, 1, x, and x squared, times p. So this is the integrand, a little 3 vector. And we're going to integrate x from 0 to infinity. And then if you've used Mathematica before, you have to tell it some things so that it doesn't give you overcomplicated answers. We have to tell it the assumption that sigma is a parameter greater than 0, and then it's also a good idea to say generate conditions equals false. Don't tell me more than I really want to know. And here's the answer it gives out. The 0th moment, that is to say the integral of 1, is 1. That's a relief. That shows that we typed in the distribution correctly, or suggests that we typed in the distribution correctly and we got the correct area. The interesting things are this first moment, which is the mean, and you can see that this is exactly this. And then the second moment, which is not the variance, because remember, the variance is the mean of the square minus the square of the mean. So let's work that out. Moments 3, that is to say the third component of our answer here, I should say here, minus moments 2 squared, that's the square of this, the mean, and simplify it, and lo and behold we get this formula, which if you look at it is exactly this formula. The gamma distribution is a very important distribution. It's defined for positive values of alpha and beta. But the way to think about it to get an idea of what it is imagine that alpha is greater than 1. The probability distribution is a power of x to the alpha minus 1 times an exponential that decays with a rate determined by beta. So the basic idea for alpha greater than 1 is that with increasing x, it's going to start at 0. Let's pick one of these gamma curves, maybe this one. It's going to start at 0 and increase as a power law until the exponential cuts in. And when the exponential cuts in, the exponential is going to dominate the power law and force it to decrease again down to 0. Okay, so that's the general behavior, and then these factors in front, as usual, are a normalization. You can compute the mean and variance of the gamma distribution, and they turn out to be these 2 combinations of alpha and beta. So generally speaking, you can find a gamma distribution that has any desired mean, that is to say, the location of its center, and any desired or many desired variance by choosing this combination of alpha and beta, and that controls the width. When alpha is greater or equal to 1, the distribution is the way I've described, namely it starts at 0 and goes to a single mode, and the location of that mode is given by this formula in terms of the parameters. So the gamma distribution here on this page and the log-normal distribution on the previous slide are both probability distributions that have two parameters, and those two parameters can be used to fit for the location of a peak of the distribution and a parameter that indicates how fast the tail will fall off, a scale parameter for the tail. Now note that although there's a scale parameter for the tail, that is to say, you could set the variance of the overall distribution, neither of these has a separate parameter that controls the functional form for how the tail decays. All gamma distributions, the tail decays exponentially. You can't get a power law distribution within this framework, within the gamma function framework. And a log-normal distribution has this funny function. It's the normal distribution in the log, so it decays as a negative exponential of the square of a log. Here's a distribution that looks a little odd when we write it down, but it's one that we're going to use quite a lot. It's called a chi-square distribution. The odd thing about chi-square is there's no chi, there's only chi-square. You're supposed to view chi-square, which is this symbol here, as being a single variable. So we say that a chi-square value is drawn from a chi-square distribution, and that distribution has a single parameter nu, which is greater than 0, if the probability of chi-square d chi-square, and here I put a d chi-square on this side, is equal to this probability density function that's shown here. In the previous slides, we haven't written a dx on both sides because it was obvious. But here I want to emphasize that you don't try to convert this to a d chi or something. It's a distribution in chi squared. Now what distribution is it? Well, let's look here. We have chi squared, and it's to a power which is set by the parameter nu. And then we have an exponential that falls off at this rate, which isn't particularly set by nu. It's just a fixed constant, a half. Well, this is just a gamma distribution, isn't it? Because the gamma distribution is the most general distribution that has a power here and an exponential here. And if you go back to the previous slide and stare at it, you'll see that the chi-square distribution is just a special case of the gamma distribution. In fact, it's gamma with parameters nu over 2, a half. In fact, here's the half right here, as we've mentioned. The chi-square distribution in general has a mean and a variance. The mean is given by nu, and the variance is given by 2 nu. When nu is greater than 2, this function has a single mode or peak, and that's located at a value nu minus 2. So notice there's a slight difference here. The mean is at nu, but the mode is at nu minus 2. And those continue to differ only by 2, even if nu becomes a large number, so that the fractional difference becomes very small. So let's recap. When we're doing computational statistics and we encounter these kinds of distributions and we want to compute with them, there are a few things that we need to have a convenient way of computing. We need the probability distribution, as we've been calling it. The more formal name that it's usually called is a PDF, a probability density function. We may also need to know the area under the curve to certain points. So that's called the cumulative distribution function, or CDF. And if the PDF is written lowercase p of x, the CDF is often written capital P of x. And here's its definition. It's simply the integral from minus infinity, or wherever the distribution starts, to x of the PDF. So it's the indefinite integral of the PDF. We also very often will want to know a function which is the inverse of the CDF. So if this is capital P of x, this is x of capital P. Do you see what question that answers? That would answer a question like, what value of x is the 90th percentile? We'd put 0.9 in here, and we'd want to know what value of x makes the area under the curve to the left of that value of x equal to 0.9 for the 90th percentile, or 0.5 for the 50th percentile, and so on. So that's a very convenient thing to be able to do. And then we'll get to, a little bit later, that we want a computational method for actually drawing random numbers, random deviates they're called, from a distribution of interest. Most computing libraries or computing workbenches like Mathematica or MATLAB have built-in functions for essentially all of the distributions we've already talked about. I'm of course partial to the code in Numerical Recipes, and here's how they're structured in Numerical Recipes. Numerical Recipes has a class, NormalDist, for normal distribution. That class contains a constructor where you say, I'm going to want to do things with a normal distribution with a certain value of mu and a certain value of sigma, and it offers you the default values of 0 or 1, but you can overrule those with whatever you want. And then it gives you member functions that let you get p of x, the probability density function, CDF of x, as the name implies, the cumulative distribution function, or inverse CDF of now P, this would be capital P, which is the inverse of the CDF function. MATLAB, for example, has function called, here's just one example for chi-squared PDF, that's the PDF, chi-squared CDF, that's the CDF, and chi-squared inv, which is the inverse of the CDF.